Well, we're going to get into two modules now that cover electrochemistry. And electrochemistry is often referred to by chemists as redox chemistry, where redox, the RED stands for reduction and the OX stands for oxidation. And we'll get into exactly what these terms mean here in the next day or so, because this is what the basis of electrochemistry is. It's a series of oxidation reduction reactions. Now, if you don't remember what that is from your first year chemistry course, that's okay, because we're going to go back over it again. And in fact, most of what we do today should be review as well, because what we're going to be doing today is assigning oxidation numbers to atoms so that we can then go into the next step, which is figuring out what's oxidized and what is reduced. But I think I'm getting ahead of myself a little bit. When we assign oxidation numbers, the first thing to understand is that an oxidation number is not actually a real number. It is a what if type of number. It is a number that says what happens if the most electronegative elements took all of the electrons for themselves. What would the charge be? That isn't true, because we know that there's a vast majority of molecules that have covalent bonds in them. So again, this is a what if type of scenario. What if the electrons were all transferred? Then what would the charge be? So that's why we're not going to call these charges. We're going to call them oxidation numbers, because they're imaginary. But what they do is they help us to understand the chemistry behind what's going on in a lot of these electrochemical reactions. Again, we covered this in your first year course, so if you're a little bit rusty, we'll go through some examples to help you remember. There are a series of rules on page 264 in your text, and as the author says, there are some rules that are always true, there are some rules that are usually true, and then you have rules that are like, well, when all else fails, let's do this and hope we can figure the rest of it out. Unfortunately, that's the way redox chemistry is, because oxidation numbers aren't always consistent for an element from one compound to the next. They will change on us, okay? So we're going to use the rules that we are sure about to figure out the rules and the oxidation numbers on the elements that we're not so sure about. So we're going to go through the examples in 9.1, and I'm going to throw a couple of other examples up here as I go through this to maybe illustrate the rules a little bit more fully. So first, what we're going to look at are when I have just an atom or a single type of atom involved in a molecule by itself. So if I have a diatomic molecule of hydrogen. The oxidation number for an element that is by itself, whether it's one atom or whether you've got a couple of them hooked together in a molecule, like for hydrogen, your other diatomic molecules, oxygen, nitrogen, fluorine, chlorine, bromine, iodine, all of those are diatomic. But the atom is by itself, and so the oxidation number for an atom that's by itself is going to be a 0. It would be the same thing if I had, say, just an atom of magnesium. If it was by itself and it wasn't bonded to anything else and it didn't have any other type of charge written on it, then the oxidation number for that is also going to be a 0. Now, on the other hand, if I have an atom and there is a charge written on it, so this is probably going to be an aqueous solution like we've been talking about with some of our solution chemistry. Since there is a charge written on this atom, that charge is also going to be the oxidation number for this particular atom. So if this is a +2 ion of iron, the oxidation number is also going to be a +2. I prefer to write my oxidation numbers up above the symbol for the element, and I feel like that makes it easier when we get into long reactions where I'm trying to see what happens to that oxidation number as we go through the reaction. So that's why I tend to write mine up above like that, so I can track changes as I go through a reaction. Okay, the next couple of rules that he mentions are for your group 1A and 2A metals. So he says that anything in 1A is going to be a +1, and anything in 2A is going to be a +2. So calcium is a metal that's in the 2A column, and therefore it is going to have a positive 2 oxidation number, okay? When I get to oxygen and hydrogen, I have rules where, as he puts it, these rules are usually true, but there's a couple of exceptions. And oxygen and hydrogen are both that way. So for hydrogen, we'll start with that one. Hydrogen is almost always a positive 1, unless it's combined with a metal, and there's nothing else combined with the metal but the hydrogen. So as an example, if I have sodium hydride, okay? Sodium is in the 1A column, so I know it's going to have an oxidation number of a positive 1, but because the hydrogen is with a metal, in this case, the hydrogen is going to have an oxidation number of negative 1. If I had something like magnesium hydride, now up here, the magnesium was by itself, and so its oxidation number was 0. But here, the magnesium is combined with a hydrogen, and because it's combined with something else, now the oxidation number is going to be a positive 2, and the hydrogen, because it's combined with a metal and with nothing else, will have an oxidation number of -1. You'll notice that what is also true about this is that the numbers here are going to add up to 0. Positive 1, negative 1 add up to 0. I have a positive 2 here, but I have 2 negative 1s, which is a negative 2 and positive 2 add up to 0. So whenever I get these oxidation numbers, they have to add up to 0 when I'm finished, unless there's a charge written on it, which I'll get to an example like that over here in a second. So now, when I get back to our original example, this hydrogen, it is combined with a metal, but there's also an oxygen in there too, so it doesn't fit in this category, so this hydrogen will have an oxidation number of a positive 1. How about oxygen? Well, normally, oxygen is going to have an oxidation number of a negative 2. There is one exception, and the exception is if you have a molecule of hydrogen peroxide. In hydrogen peroxide, the hydrogen is going to have an oxidation number of positive 1, but the oxygen is going to have an oxidation number of negative 1. And so here you can see I've got 2 positive 1s, which makes a positive 2, 2 negative 1s, which makes a negative 2, positive 2 and negative 2 adds up to 0, okay? So only if you have a peroxide is the oxygen going to have a charge of negative 2. All other times, this is going to have an oxidation number of negative 2, okay? So negative 1 if it's in a peroxide, negative 2 every other time. Now, there are a couple of different ways that you can add this up to make sure that everything adds up to 0. If you will recall, when you memorized your polyatomic ions, hydroxide had a negative 1 charge on a polyatomic ion. Well, a negative 2 and a positive 1 does make a negative 1. And I have 2 of them, which is negative 2, to balance with the positive 2 of the calcium, okay? So this isn't completely unlike balancing a formula. It's very, very similar. The difference is that I'm going to have an oxidation number for every single atom that's up here. The other way to think about this is I have 2 oxygens with a -2, 2 hydrogens at a positive 1, so that makes -4 and positive 2, and here's another positive 2, and then all of that will add up to 0. So you can think about it either way. Either way is fine. Okay, let's go over here, and I'm going to look at this one next, because this one is probably the most similar to what we've already been doing. We have sodium, which it's in the 1A column, so it's going to have an oxidation number of a positive 1. And you're going to have oxygen, which we know is going to have an oxidation number of a -2. The difference now, though, is that before we ever started, there is a negative number on this, a -1. And so that means when I get finished, all the oxidation numbers have to add up to a -1. Sulfur is one of those elements that is going to change its oxidation number all the time. And so I have to look at what it's combined with to figure out what its oxidation number is in this particular compound. So I have a positive 1 for the sodium. I have 4 oxygens at a -2, which makes a -8. a -8 and a +1 is a -7. But when I get done, I need an overall charge of -1. So that means that if I do that arithmetic, that this sulfur is going to have an oxidation number of a +6. Okay, so when I do that, I've got -8, +6, +1. All that will add together to make a -1 charge on the molecule as a whole. Okay, so these charges are going to affect, the oxidation numbers are no longer going to add to 0. Now they have to add up to whatever the charge is. Okay. One of the other rules that he gave you was for fluorine, and it said fluorine is always going to have a -1 charge. Okay, so there's a -1, I'm sorry, not a -1 charge, but a -1 oxidation number. We know that oxygen is going to have a -2 oxidation number. And so again, I'm just going to have to do some arithmetic. There was no charge written on this molecule, so everything's going to have to add up to 0. I have a -2 for the oxygen. I have a -1, and I have 2 of them for the fluorine. So that's -2 plus -2 is -4. So that means that the carbon stuck here in the middle is going to have an oxidation number of a +4. Okay, so it all adds up to 0. Carbon is another one of those ones that is going to constantly change its oxidation number. From one compound to the next, you never know what it's going to be. So you pick out the ones that you do know, and you use arithmetic to figure out the ones that you don't. Okay? How about this guy down here, C2H4? Well, the hydrogen is it with a metal? No. So since it's not with a metal, that means the charge on this one is going to be, not the charge, I'm sorry, the oxidation number. I keep flipping those around, and so we need to be careful with that. The oxidation number for hydrogen is going to be a +1, and I have 4 of them for a total of +4. The carbon has to balance that, so it's got to contribute a total of a -4, but I have 2 of them to do the job, so each one is going to have an oxidation number of a -2. Okay, so 2 times -2 is -4, 4 times +1 is +4, so they will add up to 0. So here's an example of an oxidation number changing. Here, carbon has an oxidation number of +4. Down here, it's got an oxidation number of a -2. That's a huge difference. So again, you just have to use arithmetic to make sure you get the right answer for those. Finally, we'll go down here and we'll check this guy out. Magnesium, being in the 2A column, is going to have an oxidation number of a +2. Bromine can change, but most often it's going to have an oxidation number of a -1. So what does that leave me? Well, I got a total of -4 here and a total of +2 here. So -4 plus +2 is -2. So that means the cobalt is going to have to contribute a +2. Okay. Again, the ones that you're doing for your homework are going to be very specifically chosen so that you're going to be able to figure them out. There are some that honestly are almost impossible to figure out, but we'll have a way later for I'll show you how to deal with that if it's necessary. Okay. So you do need to have the rules that are in here pretty much memorized so that you can look at any compound and say, okay, I know what the rules are. I know how to assign oxidation numbers to all of these particular atoms. All right. So I'll let you practice that for your homework today.